Hello, I'm Constantinos Kyprianou, and I am going to present my experimental findings that were undertaken at Imperial College London on sheathed cold-form steel studs under both compression and bending. Typical examples of cold-form steel frames are illustrated in the two photographs above, courtesy of Ayrshire Metals. External plasterboard sheathing is shown in the photograph on the right. Similarly, vertical members, known as studs with service holes in the web of members, are shown on the left photo of a frame during construction, while on the right photograph, cold-form steel frames sheathed with oriented strand boards, or OSB, are illustrated. A cold-form steel frame is made out of studs, the columns, which are set in a horizontal track member at the ends. The studs are typically braced at mid-level by additional horizontal members. Typical sheathing used in construction and considered in this study are plasterboards and OSB. A load-bearing sheath stud should be able to withstand compression load due to overhead action and resist lateral action about its major axis, which can be the result of forces such as wind. A member under combined effect of both of these forces is said to behave as a beam column. There can be another action acting in the minor axis of the column, again as a result from lateral actions such as wind or seismic forces, where the whole wall can resist them acting in a diaphragm action, but this is not considered in the current study. Bracing members are typically used in the industry to restrain global buckling. One of the main objectives of this study is to illustrate that restraint can also result from the presence of sheathing, which its fixity on the stud depends on number of screw connectors, the type of board material, and the type of connector fixings. A series of full-scale tests on single sheathed studs under combined compression were carried out. A total of 17 member tests were conducted, with 8 specimens subjected to pure compression, 6 combined compression and bending, and 3 to pure bending. 6 of the specimens under pure compression were sheathed with plasterboard and 2 with OSB. For the specimens sheathed with plasterboard, 4 connector spacings were examined, connected at 600, 300, 150, and 75 mm, while for the specimens sheathed with OSB, only the 2 extreme spacings of 600 mm and 75 mm were studied. Following testing of the plasterboard specimens under pure compression, and since pull-through failure was prominent, it was decided that the specimens to be tested under combined loading and pure bending would be sheathed with OSB only, with connectors spaced at 675 mm only. 6 tests were conducted under combined load, where the axial level was set to 75, 50, and 25% of the stud compression resistance, which had been determined based on the 2 tests with OSB sheathing under pure compression. The tested members were sheathed with the same type of board and using the same number of screws on both sides. The specimens were tested in a dual actuator rig. Axial compression was applied to the overhead track by a vertical actuator, while bending was applied by laterally loading the sheathing using a 4-line 2-tier wiffle tree system connected to a horizontal actuator in order to approximate a uniform distributed load. The height of the stud was 2.4 meters, the width of the sheathing 600 mm, while the length of the tracks of the tested specimens was 800 mm. The connection between the stud and the track was constructed as shown on the photo on the right. The boundary conditions and the member ends are derived from the direct contact between the column ends and the web of the track. As such, the ability for the column ends to rotate depended on the applied axial load level. For low axial load levels, the boundary conditions were approximately pinned, while for higher axial load levels, increased end fixity arose. Specimens in pure compression behaved like fully fixed ended. The stud members of 2.4 meters in length consisted of 3 service holes along their length as shown in the top photo illustrating the specimen. The specimens were C-lift shaped, 150 mm deep, 44 mm wide, and 1.5 mm thick. The steel's material yield strength was determined as 482 MPa with the use of tensile coupon tests. It is also worth mentioning that a series of material tests were carried out for both types of sheathing, OSB and plasterboard, to determine the material properties, as well as a series of pull-through tests and push-out tests to determine the capacities of screws in a sheathing to steel component system. A test rig for measuring initial geometric imperfection was designed and built. The rig was composed of 7 LVDTs shown on the right, which ran on aluminum cast rails shown on the left, calibrated to remove any inherent imperfections, allowing to measure the variation of the cross-sectional shape of the stud along its length. The initial geometric imperfections are split into cross-sectional and three global buckling modes. The cross-sectional sketches show how the amplitudes of these geometric imperfections were measured, while typical examples of how these measurements varied along the length of the specimen are shown in the two graphs on the right. Measurements were carried out for 10 specimens with service holes and 10 without. The table summarizes the average results for each set of these results. The measured imperfection amplitudes for the members with and without holes show no significant discrepancies for the local, distortional, torsional, and global major axis flexure modes. Conversely, both the magnitude and direction of the minor axis blow imperfections were affected by the presence of the holes. This is attributed to the influence of the hole punching process. The animation on the right, in a speeded up format, shows how the specimen under combined loading or pure bending during testing were laterally loaded until failure, which takes place about at this point now. A summary of the pure compression test results is shown here, where the failure load PU is plotted against the plot spacing of connectors. Substantial increases in capacity can be observed with decreasing connector spacing from 600 to 75 mm, with a 15% increase attained for the OSB sheet specimens indicated with the red line, and about 25% increase on average for the plasterboard sheet specimens indicated with the black line. Note the repeated tests for the plasterboard sheet specimens and the average line to highlight the trend in the data. For all the specimens connected at 300 and 600 mm intervals with plasterboard, pull-through failure of the connectors took place. For the plasterboard sheet specimens connected at 75 mm and both OSB sheet specimens, no connector failure was observed. The axial load displacement curves for the OSB sheet specimens are shown in the figure on the left, while the corresponding curves for the specimen sheet with plasterboard are shown on the right. The discontinuities that can be seen in the specimen sheet with plasterboard at spacing of 600, 300, and 150 mm correspond to failure of individual connectors. All of the combined loading results can be presented in a single figure, with the ultimate compression loads plotted against the ultimate horizontal loads. The black line designates the OSB sheet specimens with connector spaced at 600 mm, and the red line the specimens connected at 75 mm intervals. Increased capacities in both compression and bending between 15 to 20% were attained when closer spaced connectors were employed. It should be mentioned that the capacity of the specimens tested under pure bending was limited by the strength of the connection between the track and the column. The dominant failure mode of the OSB sheet beam column specimens was local failure at the service openings and at the ends of the members, as shown in the photographs on the left and right. Using the test data, brief comparisons can be made with the current Eurocode 3 provisions. The combined results are presented now in a normalized form, with the loads normalized against their cross-sectional resistance in compression and major axis bending respectively, with the horizontal test load converted to bending in accordance with the loading conditions in the tests. The cross-sectional resistance were determined following the effective width method given in Eurocode 3. The test results are compared against the compression bending interaction formula provided in Eurocode 3 for bare steel stud columns, which is the typical design assuming sheathing is ignored. The test results are about 4 to 5 times as much as the capacities given by this equation and assuming no effect from sheathing. Assuming bracing at mid-level, which is what is typically done in current design practice for an all-steel core foam steel frame, the effective length about the minor axis is reduced to half. But still, comparing this design to the test results where no mid-bracing exists and all restraint or extra strength is provided by the presence of sheathing is considerably underestimated. Recognizing a restraint about the minor axis of an effective length equal to the connector spacing leads to about 300% increase and much better estimations to the test data. As discussed before, in pure compression, the end boundaries behave more like fixed-ended. As such, an effective length about the major axis of half this length may be assumed. Assuming an effective length of half length about the major axis for pure compression, only an effective length about the minor axis equal to connector spacings for both compression and bending leads to further 5 to 10% improvements in compression. As it can be seen, the accuracy of the resistance predictions given in Eurocode 3 is, however, limited by the shape of the interaction curve, since the concave nature of the curve arising from the value of the powers 0.8 does not match the convex trend of the test data points. Also, further improvements can be made, especially on the bending capacity, by recognizing composite action. Finally, certain conclusions can be made. Significant improvements can be gained by recognizing the structural effect of the sheathing through bracing and fixity, while there is potential for further improvements by recognizing composite action and the convex shape of the beam-column interaction test data. All this, of course, assuming connector capacity is adequate. Findings show that typical connectors with OSB this can be achieved, while for plasterboard design needs to be more conservative by using either more connectors or better connectors. Thank you.